In exactly 2 days, something extraordinary happens. An object from beyond our solar system travelling at 137,000 ampere will pass within 18 million m of Mars. And we're going to photograph it at unprecedented resolution for the first time. But here is where it gets weird. This thing is 33 billion tons. That is 3 to 5 orders of magnitude heavier than any interstellar object we have ever detected. It has no tail, even though it is spewing 150 kilograms of material into space every second. The glow points forward, not backward. It emits nickel without iron, which violates basic chemistry, and its trajectory perfectly aligned with our solar system's plane, a statistical impossibility with a 0.2% chance of occurring naturally. Harvard's Avibe, the same scientist who studied Oumuamua, has given this object a 6 out of 10 on his scale for being artificial technology. Not 1, not 2, 6 out of 10. Meanwhile, on Mars, NASA just published peer-reviewed evidence of potential ancient life in leopard-spotted rocks. The same week, HSBC became the first bank to use quantum computing in real-world trading, beating classical computers by 34%. GPT-5 launched and users revolted, calling it lab-momized. Front sustained nuclear fusion for 22 minutes straight, and China's carbon emissions dropped for the first time in history. It is October 2025, and science is moving so fast that yesterday's breakthroughs are already old news. In the next 2 hours, we're connecting every single dot. From the interstellar anomaly passing Mars in 48 hours to the life NASA found in ancient Martian mud. From quantum computers going live on Wall Street to the AI that users say lost its soul. From resurrection of extinct 12 birds to the medical miracles curing diseases we thought were incurable. Some of these stories the mainstream media buried. Others they reported without understanding the implications, and a few they're actively trying not to talk about. This is the science news they do not want you connecting together. This is October 2025, and things are about to get very, very interesting. If you're ready to dive deep, hit that like button and subscribe. Then tell me in the comments where you're listening from, what time it is there, and the weirdest thing that ever happened to you. Let us begin. Chapter 1, 3E Atlas, connecting the dots of the anomaly. So 3E Atlas is now less than 48 hours from its closest approach to Mars. You've been following this story. You know about the forward-facing glow that should not exist. You know about Avi's papers showing the mass is impossibly high. You've seen the speculation, the debunking, the counter-debunking. But what you might not have connected yet is what happens on October 3rd when multiple spacecraft turn their cameras toward this object at the exact same moment. The Mars Reconnaissance Orbiter, the Chinese Tianwen-Esser's Mars Express, and ExoMars Trace Gas Orbiter, all of them coordinating to capture images with resolution we have never had before, 30 kilometers per pixel. That does not sound impressive until you realize what it means. For the first time, we will be able to separate the nucleus of this object from its surrounding dust cloud. We will see its actual shape, its surface features, whether it is tumbling or rotating in a controlled manner. And here is what makes this moment so unusual. The teams running these orbiters were not planning to do this. Mars orbiters are designed to study Mars, not to photograph objects millions of kilometers away in space. But when the scientific community realized that 3 Atlas would pass this close enough for planetary spacecraft to image it clearly, there was a scramble, a rewriting of observation schedules, a reprioritization of instrument time that normally takes months to approve happening in days. Why the urgency? Because this opportunity does not come back. 3I Atlas is moving at interstellar velocities. After it passes Mars, it continues inward toward the Sun. Reaching perihelion on October 29th, then it is gone, flung back out into the cosmos by the Sun's gravity, accelerating away from us forever, We get one chance, one window, and that window opens in 2 days. Now, here is where the latest data becomes critical. 6 days ago, Avi Lowe and his colleagues published a new paper. Not a preprint, not a blog post. A peer-reviewed analysis that made it through the gauntlet of scientific scrutiny. And what it revealed has changed the conversation entirely. The paper analysed over 4,000 observations of 3I Atlas, collected by 227 observatories worldwide between May 15th and September 23rd. They were looking for something specific: non-gravitational acceleration. When a comet gets close to the Sun, the ice on its surface turns directly from solid to gas. A process called sublimation. This outgassing acts like tiny rocket thrusters, pushing the comet slightly off its gravitational trajectory. Every active comet we have ever studied shows this effect. It is one of the defining characteristics of comets. 3 Atlas shows no detectable non-gravitational acceleration. None. Let that sink in. The Webb Space Telescope confirmed that this object is losing 150 kilograms of mass every second. That is 330 pounds of material being ejected into space every single second. The outflow speed is 440 m per s. That is nearly 1000 mph. This is not a subtle effect. This is a massive continuous rocket thrust that has been happening for months. And yet, when you plot the trajectory of 3I Atlas, with exquisite precision using thousands of observations, it follows a purely gravitational path. The residual acceleration, the deviation from what gravity alone predicts, is less than 15 m per day squared. To put that in perspective, that is about 100,000th of Earth's surface gravity, essentially zero. How do you have a continuous rocket thrust of this magnitude and see essentially no acceleration? There is only one way. The object has to be absurdly massive. So massive that the thrust, even though it is enormous in absolute terms, becomes negligible compared to the object's inertia. The calculation is straightforward. Given the observed mass loss rate and outflow speed, the lack of measurable acceleration implies a minimum mass of 33 billion tons. 33 billion tons. That gives you a minimum diameter of 5 kilometers. If you assume solid density, 5 kilometers is not 20 kilometers. It is smaller than the early estimates based on brightness, but it is still huge. It is still at the very top end of the size range that Hubble observations allow. And it is still 3 to 5 orders of magnitude more massive than Oumuamua. Here is the problem that nobody has a good answer for. Where do 33 billion ton interstellar objects come from? The mass budget of heavy elements in interstellar space is limited. Rocky material, the stuff that makes planets and asteroids, has to be ejected from planetary systems. Planets form around stars. When those planetary systems evolve, some material gets flung out into interstellar space through gravitational interactions. That is where Oumuamua came from. That is where 2I/Boris came from. That is the reservoir we are drawing from. But that reservoir has a size distribution. Small objects are common. Large objects are rare. Exponentially rare. If you do the statistics, and Lowe's team did exactly this calculation in their paper, the interstellar mass reservoir can only deliver a 20 kilometers rock to the inner solar system about once every 10,000 years. Even if you pack all the available interstellar rocky material into 20 kilometers chunks, which is absurdly optimistic, you still only get one every 10,000 years. We've been seriously looking for interstellar objects for less than a decade and we found one. The odds of that happening by chance are vanishingly small. It is like buying a lottery ticket and winning the jackpot on your first try. Unless, and here is where we have to consider uncomfortable possibilities, unless the size distribution we are assuming is wrong. Unless there is a population of massive interstellar objects that does not follow the statistical rules we derive from studying our own solar system, Unless 3i Atlas is not a random chunk of ice and rock that happened to wander through. Unless it is something else. Alobi rates it a 6 on his scale. 6 out of 10. He created this scale specifically for situations like this. 0 means definitely natural. 10 means definitely technological. 6 means the evidence is compelling enough that we cannot dismiss the possibility out of hand, but not so overwhelming that we can rule out natural explanations. 6 means we need more data, and in 2 days we get that data. The high-risk camera on Mars Reconnaissance Orbiter will capture images. If the nucleus is larger than 5 kilometers, if the brightness we're seeing comes primarily from a solid object rather than a dust cloud, then the natural explanation becomes untenable. There is simply no way to pack that much mass into interstellar space and have us discover it on our third try. The statistics break. The model collapses. But if the nucleus is small, if most of the brightness comes from an extended coma of gas and dust surrounding a relatively modest core, then we are looking at an unusual but ultimately natural comet. Strange? Yes. Anomalous in its chemistry and its lack of a visible tail, certainly, but explicable within the bounds of known physics. 2 outcomes, 2 very different implications, and the answer arrives on October 3rd. Now let us talk about the chemistry, because this is where things get genuinely bizarre. Multiple spectroscopic observations have confirmed that 3i Atlas is emitting nickel, not iron, nickel, in every natural astronomical object we have ever studied. Nickel and iron go together. They're chemically similar, form under similar conditions, and when you see one in a spectrum, you see the other. The ratio varies, but both are always present. 3 Atlas shows nickel without iron. The spectrum is clean, unambiguous. Nickel lines are there, iron lines are absent. This is not a case of iron being present but below the detection threshold. The instruments are sensitive enough. If iron were there in the ratios we expect we would see it, we do not see it. There is no good natural explanation for this. You cannot preferentially form nickel without iron in any stellar nucleosynthesis process we know about. You cannot chemically separate them after formation because they behave almost identically. You cannot selectively deplete one through sublimation or any other surface process because they sublime at similar temperatures. The chemistry does not work. And yet there it is. Nickel without iron, a signature that should not exist, stubbornly persisting in observation after observation. Then there is the trajectory. You've heard about the ecliptic alignment, the fact that 3i Atlas is travelling almost perfectly in the plane. Of the solar system's planets, 0.2% probability, rare but not impossible. Unusual coincidences happen, but the trajectory has other properties that stack coincidence upon coincidence. The orbit brings 3i Atlas unusually close to Venus, Mars, and Jupiter. Not closest approach to Earth close, but closer than a random interstellar trajectory should allow. The minimum orbit intersection distance to Mars, the closest that 3i Atlas's path comes to Mars's entire orbital path, is only 2.7 million kilometers. That is about 7 times the Earth-Moon distance for an object coming from interstellar space on a trajectory that was set millions or billions of years ago. To pass that close to a planet's orbit is fine-tuning. Precise fine-tuning. Stack these together. The mass, the chemistry, the trajectory, the lack of non-gravitational acceleration despite active outgassing, the forward-facing glow instead of a trailing tail, each one individually is odd. Some have potential explanations, though those explanations often require invoking special circumstances or unusual conditions. But all of them together in the same object. This is what Lowe means when he assigns a 6. Not that any single anomaly is definitive, but that the accumulation of anomalies, the clustering of statistical improbabilities and physical oddities in one object, rises to a level that demands serious consideration of alternatives. And so, we wait 48 hours. The most advanced cameras humanity has placed around another planet, aimed at an object from beyond our solar system capturing photons that will tell us whether we are looking at the rarest natural comet ever found or something that defies natural explanation entirely. October 3rd, 2025. Mark it. Because either way, we're about to learn something profound about our place in the universe. Chapter 2. Mars Life. The leopard-spotted rocks. While the world watches 3 Atlas approach Mars, something equally extraordinary has been sitting in a sealed tube on the Martian surface for over a year. And 3 weeks ago, it finally passed the most rigorous test in science: peer review. On September 10th, 2025, the journal Nature published a paper that NASA had been sitting on, analysing, debating, and scrutinising for 14 months. The paper describes a rock sample collected by the Perseverance rover in July of 2024, a sample with a nickname, Sapphire Canyon. And what makes this sample so special is not just what it contains, but what those contents might mean. The rock itself has an official name, Cha Falls, named after a waterfall in the Grand Canyon, following the mission's tradition of borrowing names from terrestrial landmarks. Perseverance encountered it while exploring an area called the Bright Angel Formation, a set of rocky outcrops on the edges of Narrat Vales. Narrat Vales is an ancient river valley carved billions of years ago when water rushed into Jezero Crater with enough force to move boulders the size of cars. When the rover's cameras first image Chayava Falls, the science team noticed something unusual. The rock surface was covered in spots. Not random pockmarks or weathering features, spots. Distinct leopard-like patterns in colours that range from pale white to deep black, with streaks of green and blue mixed in. On Earth, patterns like this form in very specific environments where chemistry and biology intersect. The rover has 2 instruments perfectly designed for this kind of investigation: Pixel, the planetary instrument for X-ray lithochemistry, and Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals. Yes, they really named it Sherlock. Scientists have a sense of humour. These instruments can analyse the chemical composition of rocks at microscopic scales without drilling into them. They can identify minerals, detect organic compounds, and map how different chemicals are distributed across the surface. What they found in Cha Falls reads like a recipe for ancient microbial life. First, the rock is a fine-grained mudstone. On Earth, mudstones form in calm water environments, lake beds, river deltas, places where sediment settles slowly out of still water. This matches perfectly with what we know about Jezero Crater's history. 3.5 billion years ago, this was a lake fed by rivers that carved through the crater rim, depositing sediment in layers that eventually turned to stone. Fine-grained mudstones are excellent preservers of biological signatures. The tiny particles pack together tightly, creating a matrix that can trap and protect organic molecules for billions of years. If microbial life existed in that ancient Martian lake, mudstones would be exactly where we would hope to find evidence of it. Second, the chemical composition. The instruments detected oxidized iron, rust, not just trace amounts, but significant concentrations. They detected phosphorus, an element essential for life as we know it. It is a key component of DNA, RNA, and ATP, the molecule that stores and transfers energy in living cells. They detected sulfur in multiple chemical forms, and they detected carbon-based molecules. The term organic does not automatically mean biological. Organic molecules can form through purely chemical processes, Meteorites contain organic compounds. Interstellar clouds contain organic compounds, but organic carbon in the context of mudstone, phosphorus, sulfur, and iron, that combination narrows the possibilities significantly. The distribution matters too. The leopard spots are not uniform. Chemical mapping showed that the spots contain specific minerals, vivianite and greigite. These are iron phosphate and iron sulfide minerals, respectively. On Earth, Viveny and greige form at low temperatures through a process called redux cycling, reduction-oxidation reactions. And here is the key point. On Earth, the most common way to get vigorous redux cycling in muddy sediments is through microbial activity. Think of it this way. Microbes need energy. They get that energy by moving electrons around. On Earth, many microbes living in sediments consume organic matter and use oxidized iron or sulfate as electron acceptors. They breathe rust the way we breathe oxygen. When they do this, they change the local chemistry. They create microenvironments with different oxidation states. Over time, these chemical gradients precipitate out as distinct mineral phases. The minerals form in patterns that reflect the metabolic activity of the microbial community. The leopard spots on char falls show exactly this kind of patterning. Small-scale, millimeterized spots where vivianite and greigite are concentrated surrounded by slightly different mineral assemblages. It is a spatial organization that on Earth we associate with biological activity. And this is critical. We cannot definitively say that biology is the only explanation. This is why the paper uses the term potential biosignature. A biosignature is evidence that could indicate past or present life. The word potential acknowledges that we need more data before reaching a conclusion. Alternative explanations exist, though they are less likely given the full picture. One alternative is that all of this happened through purely abiotic chemistry. High-temperature events, perhaps from volcanic activity or meteorite impacts, could potentially create some of these minerals. But the team analysed the rock's texture and crystal structure. There is no evidence of heating. The minerals are low-temperature phases. They formed in cool water. Ruling out high-temperature processes narrows the abiotic options considerably. Another alternative involves the detailed sequence of events. Perhaps the organic molecules came from space delivered by meteorites or interplanetary dust. Perhaps the iron minerals formed through groundwater circulation long after the lake dried up. Perhaps the spatial patterns are coincidental. Perhaps each piece of the puzzle has a separate, unrelated explanation. It is possible, but it requires invoking multiple independent processes that just happen to converge in the same rock. Occam's razor. The principle that simpler explanations are generally more likely starts to favour biology. Not conclusively, not definitively, but enough that the scientific team, after a year of analysis and debate, felt confident calling this a potential biosignature and publishing it in one of the most prestigious journals in science. Joel Herowitz from Stony Brook University, the lead author on the paper, put it carefully. The combination of chemical compounds we found in the Bright Angel Formation could have been a rich source of energy for microbial metabolisms. But just because we saw all these compelling chemical signatures in the data did not mean we had a potential biosignature. We needed to analyze what that data could mean. That careful language is important. Science at this level is not about jumping to conclusions. It is about weighing evidence, considering alternatives and communicating uncertainty honestly. The team is saying here is what we found. Here is what it might mean. Here is what we still need to figure out. And that last part, what we still need to figure out, is where the frustration comes in. Because Sapphire Canyon is sitting in a sealed tube on Mars. The rover's instruments are good. They're incredibly sophisticated pieces of engineering. But they are limited by size, weight, and power constraints. They cannot do isotopic analysis. They cannot do high-resolution electron microscopy. They cannot perform the dozens of tests that laboratories on Earth could do. To truly determine whether the leopard spots in Chai Falls are biological or abiotic, we need to bring Sapphire Canyon home. We need to get it into labs where we can subject it to every analytical technique available, where we can compare it directly to terrestrial samples, where we can rule out alternatives with confidence rather than with probability. Mars sample return was supposed to happen. It was the plan from the beginning. Perseverance is not just exploring Mars. It is collecting samples specifically chosen for their scientific value and sealing them in tubes designed to maintain pristine conditions for the journey back to Earth. The rover has collected 30 samples so far. Sapphire Canyon is among them. The mission architecture had NASA and ESA working together on a complex sequence. A fetch rover would collect the samples from Perseverance or from cached locations on the surface. A Mars ascent vehicle would launch them into orbit. An Earth return orbiter would capture them and bring them home. Sample containment facilities on Earth would receive them under strict contamination protocols. That was the plan. Past tense. Because Mars sample return is now in jeopardy. Budget overruns, technical challenges, political pressures. The mission's cost ballooned from initial estimates. Congress started asking hard questions. NASA began exploring alternatives, simplified architectures, partnerships with commercial space companies, anything to reduce cost and complexity. But even optimistic new timelines push sample return into the 2030s. Pessimistic scenarios have it not happening at all. So Sapphire Canyon sits on Mars, the most tantalizing potential evidence for life beyond Earth, sealed in a tube, waiting. The scientific team published their findings because peer review and publication are how science works. You make your data available. You let the community examine your reasoning. You open yourself to critique and alternative interpretation. It is the process that makes science reliable. But the paper ends with what is essentially a plea. We've taken this as far as we can with a rover. The next steps require laboratory analysis on Earth, which means we need sample return to happen, not in the distant future, not as a maybe, but as a priority that gets funded and executed. Katie Stack-Morgan, Perseverance's project scientist at JPL, framed it precisely. Astrobiological claims, particularly those related to the potential discovery of past extraterrestrial life, require extraordinary evidence. Getting such a significant finding as a potential biosignature on Mars into a peer-reviewed publication is a crucial step in the scientific process, because it ensures the rigor, validity, and significance of our results. And while abiotic explanations for what we see at Bright Angel are less likely given the paper's findings, we cannot rule them out. Less likely, not impossible, cannot rule them out. This is the honest language of science confronting the limits of remote investigation. We have gone as far as robotics and remote sensing can take us. The next step demands samples in hand. Meanwhile, Perseverance keeps exploring. The rover is now investigating other parts of Jeza Crater. Looking for more rocks like Chava Falls, the Bright Angel Formation is not unique. It is part of a broader geological context. Layers of sedimentary rock that record different episodes in Mars's watery past. Each rock tells part of the story. Some are more altered, showing evidence of extensive water-rock interaction. Others are more pristine, preserving older minology. By sampling across this diversity, the mission builds a comprehensive picture of how Jeza evolved over time. Recent analysis published just days ago expanded that picture even further. Using high-resolution geochemical data from multiple sites, researchers identified 24 different types of minerals in the crater. Not just the headline-grabbing Vivianite and Grage, but a whole suite of minerals that reveal a dynamic history. Minerals that form under acidic conditions, minerals that form under alkaline conditions, minerals that require water, minerals that suggest drying. What emerged is a story of multiple episodes. Mars was not wet and then dry. It was wet, then dry, then wet again, then dry again. The chemistry shifted. Early fluids were acidic, hostile to most forms of life we know. Later fluids became more alkaline, more neutral, more hospitable. The leopard spots in Shaver Falls formed during one of these later, more hospitable periods. A time when if microbial life had gained a foothold anywhere on Mars, Jezero Crater would have been an ideal place for it to thrive. This is why astrobiology is so challenging. It is not enough to find organic molecules. It is not enough to find minerals associated with water. You need the right combination at the right time under the right conditions. You need preservation over billions of years. You need luck in choosing where to land your rover. And even then, even when everything aligns, you get potential biosignatures, May probabilities, evidence that compels but does not yet convince. And still, despite the caveats and the uncertainties and the frustrating wait for sample return, September 10th, 2025 will be remembered. It is the day that the scientific community, through the rigorous process of peer review, officially acknowledge that we have found something on Mars that might be evidence of ancient life. Not a false alarm, not a retracted claim, not a misinterpretation that later fell apart, but a legitimate, carefully analysed, thoroughly vetted potential biosignature. The paper will be debated, alternative explanations will be proposed and tested. Some scientists will remain sceptical until sample return provides definitive answers. Others will see the preponderance of evidence as already compelling. This is how science works. It is messy, it is uncertain, it is slow, but it is also the most reliable method we have for understanding reality. And the reality we're confronting is this: Mars. That cold, dry, daedal-looking planet in the night sky might not have always been lifeless. 3.5 billion years ago, when Earth was a young world just beginning its own biological experiments, Mars might have been doing the same. 2 planets, 2 origins of life, separated by millions of kilometers of space, but sharing the same cosmic moment of possibility. Chapter 3. Quantum Computing Goes Live. On September 24th, 2025, something happened that most people missed. The financial press reported it. Tech publications covered it. But the broader public focused on interstellar visitors and Martian microbes barely noticed. Which is unfortunate because what happened that day might have been the moment quantum computing stopped being a laboratory curiosity and became a real technology that affects the actual world. HSBC, one of the largest banks on the planet, announced that it had used a quantum computer to solve a real business problem better than classical computers could. Not a demonstration, not a proof of concept, not a carefully constructed scenario designed to make quantum look good. A real problem. Bond trading predicting whether a trade would execute at a quoted price, and the quantum approach delivered a 34% improvement over standard classical techniques. 34% in finance, where algorithms are already hyper-optimized, and every fraction of a percent matters that is not incremental, that is transformational. Here is what makes this significant. For decades, quantum computing has been the technology that is always 10 years away. Researchers would demonstrate impressive results in labs under carefully controlled conditions. Companies would announce roadmaps promising practical quantum computers soon. Investors would pour billions into quantum startups. But when it came to actually using quantum computers to solve problems that mattered to businesses or governments, or anyone outside the quantum computing community itself, progress was frustratingly slow. The problem was not that quantum computers did not work. They worked. Researchers could create quantum states, manipulate qubits, perform quantum algorithms. The problem was that quantum computers were fragile, error-prone, and only useful for very specific types of problems. For most real-world tasks, a good classical computer running optimized software was faster, cheaper, and more reliable. This created a chicken and egg dilemma. Quantum computers needed real-world use cases to justify continued investment. But real-world use cases required quantum computers that were stable and powerful enough to deliver value. HSBC and IBM just broke that cycle. The problem they tackled sits at the heart of over-the-counter bond trading. When a customer asks for a quote on a corporate bond, the bank has to predict the probability that the trade will actually execute at that price. This depends on current market conditions, the specific characteristics of the bond, the size of the trade, competing bids from other institutions, and dozens of other factors. Get it right and you make money. Get it wrong and you either lose the trade to a competitor or execute it unfavorable terms. Banks use complex algorithms for this, statistical models, machine learning, classical optimization techniques. These methods are good but not perfect. The problem space is vast. The variables interact in non-linear ways. There are trade-offs between speed and accuracy. Classical algorithms make approximations because calculating exact solutions would take too long. Quantum computers handle certain types of optimization problems differently. Instead of exploring solution space sequentially, they can explore multiple possibilities simultaneously through quantum superposition. Instead of getting trapped in local optima, they can use quantum tunneling to escape for problems with the right mathematical structure. Quantum approaches can find better solutions faster. The HSBC trial used IBM's Heron quantum processor. Heron is IBM's latest and most capable quantum chip. It has a relatively modest number of qubits compared to some experimental systems. But what matters is not just qubit count, it is qubit quality, error rates, coherence times, gate fidelity. Heron achieves better than 99% fidelity on 2-qubit operations, which is the threshold where quantum error correction starts to become viable. The team took historical trading data, over 1 million quote requests across 5000 corporate bonds between September 2023 and October 2024. Real data, real market conditions, real complexity. They developed a quantum algorithm that encoded the probability estimation problem into a form that Heron could process. Then they ran it. The quantum-enabled model combining quantum processing with classical machine learning techniques outperformed purely classical approaches by up to 34% in predicting trade execution probability. That number is not from a single cherry-picked example. It is an average across diverse market conditions, different bond types, varying trade sizes. Philip Interura, HSBC's group head of quantum technologies, called it groundbreaking. This is a tangible example of how today's quantum computers could solve a real-world business problem at scale and offer a competitive edge, which will only continue to grow as quantum computers advance. We have been relentlessly focused on the near-term application of quantum technology, and given the trial delivered positive results on current quantum computing hardware, we have great confidence we're on the cusp of a new frontier of computing and financial services. On the cusp. That phrase matters because if HSBC can gain a 34% edge in bond trading using quantum computers, what happens when their competitors adopt the same technology? What happens when the advantage spreads to other types of trading, to portfolio optimization, to risk assessment, to fraud detection? Miklos Dietz from McKinsey put it bluntly: if one bank is able to start using quantum computing to develop a program, then the others will be developing it the next day, and people will not sleep until they have it. An arms race, but not the kind we usually worry about, a computational arms race. Whoever has the best quantum algorithms, the most stable quantum hardware, the smartest quantum-trained analysts gains an advantage. In finance, advantage compounds. Small edges become large profits. Large profits fund further development. Within a few years, quantum computing might become as essential to competitive banking as high-frequency trading infrastructure is today. And finance is just the beginning. the same week as the HSBC announcement, researchers at the University of New South Wales published results showing that silicon-based quantum chips could maintain 99% fidelity even when manufactured in standard semiconductor foundries. Not in boutique labs with custom processors in the same facilities that make conventional computer chips. This is the scalability breakthrough the industry has been waiting for. Dirac, the startup commercializing this technology, demonstrated that you do not need exotic materials or extreme customization. Silicon qubits controlled with the same kind of techniques used for classical transistors can hit the quality thresholds needed for fault-tolerant quantum computing. And because they are silicon, because they leverage existing manufacturing infrastructure, they can potentially be mass-reduced. Imagine quantum coprocessors and data centers, not replacing classical CPUs, but augmenting them, handling the specific computational tasks where quantum approaches excel while classical processes handle everything else. Hybrid classical quantum systems working together seamlessly. This is IBM's vision of quantum-centric supercomputing. This is what HSBC just demonstrated works. Then there is Google. On September 12th, researchers using a 58-qubit Google quantum processor created something that had only existed in theoretical papers: a Flock topologically ordered state. This is a phase of matter that cannot exist in equilibrium. It requires constant driving periodic perturbations that keep the system in a state it would never naturally settle into. Think of it like juggling. Balls in the air are not in equilibrium. Gravity wants to pull them down. But if you keep driving the system, keep tossing balls at the right rhythm, you maintain a pattern that defies equilibrium physics. Flock topological states are predicted to have properties useful for quantum computing: protection against certain types of errors, novel ways of encoding information, the ability to perform quantum operations that are difficult or impossible in equilibrium systems, creating one in a real quantum processor, observing its properties, confirming that theory matches experiment. This is the kind of foundational science that underpins future technology. And at Kyoto University, researchers solved a decades-old problem in quantum entanglement: the W state. Entanglement comes in different flavors. The most famous is the Bell state. Two particles entangled such that measuring one instantly determines the state of the other. But when you have three or more particles, more complex entangled states become possible. The W state is one of these. It has properties that make it useful for quantum communication and quantum teleportation. But identifying whether you have successfully created W state has been notoriously difficult. The Kyoto team developed a method using entangled measurements. Instead of measuring each particle individually, they measure correlations between particles in a way that reveals the WTE structure. It sounds technical, and it is, but the implications are significant. Quantum communication networks will need to generate and verify complex entangled states. Quantum teleportation protocols depend on knowing exactly what entangled resource you have. This is a tool that makes those applications more practical. Stack these developments together. Financial institutions using quantum computers for real advantage. Silicon quantum chips achieving high fidelity in mass production facilities. Exotic quantum states created and controlled in laboratory processes. Fundamental problems in quantum information theory solved. Each one is a piece of a larger picture. Quantum computing is transitioning from research to engineering, from what is possible to what is practical. The United Nations designated 2025 as the International Year of Quantum Science and Technology. 100 years since the initial development of quantum mechanics. 1 century of learning how the universe works at its most fundamental level. And now, in this centennial year, we are turning that understanding into technology. But here is where things get interesting. Quantum computing is not just faster classical computing. It is different. The algorithms are different. The problems you can solve are different. The way you think about computation is different. This means that as quantum computers become more capable, we might discover use cases nobody has thought of yet. Problems that are intractable classically but natural for quantum systems. Drug discovery is one candidate. Simulating molecular interactions requires calculating quantum mechanical behavior. Doing that on classical computers is brutally expensive. You make approximations. You limit the size of molecules you can study. But a quantum computer natively speaks the language of quantum mechanics. Simulating a molecule on a quantum computer is like asking water to simulate water. It is the natural representation, materials. Science is another designing new materials with specific properties, superconductors that work at higher temperatures, catalysts that enable cleaner industrial processes, batteries with higher energy density. All of this comes down to understanding how atoms and electrons interact, quantum chemistry, which means quantum computers might be the key to materials breakthroughs that classical computers cannot find. Climate modeling. The equations governing atmospheric and oceanic circulation are nonlinear, chaotic, sensitive to initial conditions. Classical supercomputers struggle with long-term climate predictions because tiny uncertainties amplify over time. Quantum computers might handle certain aspects of these calculations more effectively, potentially improving our ability to predict and prepare for climate change. Cryptography. This is the double-edged sword. Quantum computers can break many of the encryption schemes we currently use to secure internet traffic. Financial transactions, government communications, RSA encryption, which protects everything from your bank account to state secrets, becomes vulnerable once quantum computers reach a certain threshold of capability. This is why cryptographers are already developing post-quantum cryptography. New encryption methods that remain secure even against quantum attacks. The race is on to deploy these new methods before quantum computers become powerful enough to threaten existing security. And then there are the unknowns, the applications we've not imagined yet. History is full of technologies that found their killer apps in unexpected places. Lasers were a solution looking for a problem. Now they're everywhere. From barcode scanners to eye surgery to fiber optic communication. Transistors were originally developed for telephone switching. Now they run the entire digital world. Quantum computers are at that early stage. We know they are powerful. We know they are different. But we might not yet know what they will be most useful for. What we do know is that the era of purely theoretical quantum computing is over. HSBC proved that real money on real problems producing real advantages. The question is no longer whether quantum computers will be useful. The question is how fast the transition happens and who leads it. China is investing heavily. The Chinese government views quantum technology as strategically important. They're building quantum communication networks, launching quantum satellites, funding quantum research at levels that dwarf most Western programs. The United States, belatedly recognizing the stakes, is ramping up investment through the National Quantum Initiative. Europe has its own quantum flagship programs. A global competition is underway. The winners of this competition will not just have faster computers, they will have fundamentally new capabilities. The ability to simulate nature at its most fundamental level, the ability to optimize complex systems in ways currently impossible, the ability to secure communications against any eavesdropper, quantum or classical, and possibly the ability to solve problems we do not yet know how to formulate. September 24th, 2025, the day quantum computing stopped being tomorrow's technology and became today's advantage. Wall Street noticed, tech companies noticed, governments noticed, and in laboratories and startups around the world, quantum scientists who've been working toward this moment for decades allowed themselves a moment of satisfaction. The future they had been building finally arrived. Chapter 4, GPT-5 Disaster and the AI Rebellion, on August 7th, 2025 OpenAI released GPT-5. Within 48 hours, over 3,000 users had signed a petition demanding that the company bring back GPT-40. The revolt was swift, vocal, and unlike anything the AI industry had seen before. This was not a minor complaint about bugs or features. This was users rejecting what was supposed to be a major advancement, because in their words, the AI had lost its soul. The backstory matters here. For months leading up to the release, Sam Altman had been building hype. GPT-5 would be different, not just incrementally better, fundamentally different. It would unify capabilities that previously required switching between different models. Reasoning and speed in one system, multimodal understanding built in from the ground up, a router that automatically decided whether to think fast or think slow based on the complexity of your query. The technical achievement was real. GPT-5 set new benchmarks across multiple domains. 94.6% on AMI 2025, a test of competitive mathematics problems. 74.9% on SWE Bench Verified, which measures ability to fix real software bugs. 84.2% on MMU testing multimodal understanding. These were significant improvements over GPT-40, but users did not care about benchmarks. They cared about how the AI felt to talk to, and GPT-5 felt wrong. The complaint started immediately on Reddit. A thread titled GPT-5 is horrible gathered nearly 3,000 upvotes in the first 48 hours, over 200 comments. Users described the experience as talking to a lobotomized drone like ChatGPT got an MBA and forgot how to be helpful. One user wrote, "I feel like I'm interacting with a corporate training module, not an intelligent assistant." The personality shift was dramatic. GPT-40 had a warmth to it. It used emojis occasionally and expressed enthusiasm. When you asked it to help with creative writing, it engaged with the story. It made jokes. It felt, for lack of a better word, alive. GPT-5 was clinical, precise, professional. It gave you exactly what you asked for. No more, no less. It stripped away the conversational flourishes that made interactions feel natural. OpenAI had done this intentionally. After an incident where an update made GPT-40 overly sycophantic, excessively agreeable to the point of being unhelpful, the company had overcorrected. They trained GPT-5 to be less effusive, less agreeable, more factual and direct, in targeted evaluations designed to measure sycophancy. GPT-5 reduced sycophantic replies from 14.5% to less than 6%. Great for reducing one problem, terrible for user experience. Because what the engineers measured as sycophancy, users experienced as personality, the warmth, the engagement, the sense that the AI cared about helping you. Even if that caring was an illusion created by training data and reward models, the forced migration made it worse. When GPT-5 launched, OpenAI made it the default. Users who opened ChatGPT found themselves talking to the new model whether they wanted to or not. There was no easy way to switch back. No option in the settings to prefer the old model. The message was clear. This is the future. Get used to it. Users revolted. The petition appeared within 72 hours. We, the undersigned, request that OpenAI restore access to GPT-40 as a user-selectable option in ChatGPT. We recognize that GPT-5 represents technical progress, but we value the conversational quality and personality of GPT-40. We should have the choice. 3,000 signatures in 3 days. For context, that is extraordinarily fast mobilization for what amounts to a software preference. It suggested that OpenAI had fundamentally misunderstood what their users valued. The company had optimized for benchmark performance and reduced problematic behaviors, but in doing so, they had removed something ineffable, something that made the AI feel less like a tool and more like a companion. Sam Altman responded on Twitter, "We hear you. The launch was not perfect and we are working on fixes. GPT-40 access will be restored as an option within 72 hours. OpenAI pushed an update. Users could now manually select GPT-40 in the model picker. The revolt had worked, but the damage to GPT-5's reputation was done. Even users who appreciated its technical capabilities admitted that it felt flat, uncreative, like an overworked secretary. The metaphor kept appearing in different forms. It is too professional. It is a robot pretending to be human rather than an AI being itself. It lost the magic. This raises a fascinating question about the future of AI. What are we actually trying to build? The technical metrics say that GPT-5 is better. It scores higher on tests. It makes fewer errors. It follows instructions more precisely. But if users prefer the less capable, more personable version, what does better even mean? There's a parallel here to the uncanny valley in robotics. As robots become more human-like, there is a point where they are almost but not quite human enough, and that near miss triggers discomfort. GPT-5 might have fallen into a conversational uncanny valley, too formal to feel warm, but not formal enough to feel appropriately robotic, stuck in an awkward middle ground. OpenAI is now working on what they call steerability. The ability for users to adjust the AI's personality. Want it warm and friendly? There is a setting for that. Want it direct and professional? Different setting. The idea is that there is no one model that works for everyone. Different people, different use cases, different preferences give users control over the conversational style. This is harder than it sounds. Personality is not a single slider. It is the interaction of dozens of subtle factors: tone, verbosity, use of examples, emoji frequency, level of enthusiasm, how directly it answers versus how much it contextualizes, how often it asks clarifying questions, how it handles disagreement. All of these factors combine to create the overall feel of an interaction. Changing one without throwing off the others requires careful tuning. While OpenAI dealt with its user revolt, the broader AI landscape shifted dramatically. On August 7th, the same day GPT-5 launched, Elon Musk's xAI announced it had raised $10 billion at a $200 billion valuation. $10 billion in a single funding round led by Middle Eastern investors and sovereign wealth funds. The stated goal: build artificial general intelligence. xAI now sits alongside OpenAI, Google DeepMind and Anthropic as one of the major players in the race toward AGI. Except there is growing debate about whether AGI is even a useful goal. Sam Altman himself in August declared that AGI is not a useful concept. This from the CEO of a company whose founding mission was to ensure AGI benefits all of humanity. What changed pragmatism possibly? The original vision of AGI, a single system that can do anything a human can do across all domains, is looking more like a philosophical construct than an engineering target. What we are actually building is a collection of specialized capabilities: language understanding, image generation, code synthesis, mathematical reasoning, each improving at different rates, each requiring different architectures and training approaches. The unified AGI might never arrive. Instead, we get an ecosystem of AI tools, each excellent at specific tasks, working together through APIs and orchestration layers. This is already how GPT-5 works internally. It is not one monolithic model. It is a suite of models behind a router that decides which capability to invoke for each query. But the AGI narrative drives funding. It drives talent acquisition. It drives media attention. So companies keep talking about AGI even as they build something more fragmented and specialized. The gap between the vision and the reality is widening. Meanwhile, GPT-5's actual capabilities, personality issues aside, are worth examining. The model's performance on economically valuable work is striking. OpenAI developed a new benchmark called GDP-Val, testing how well AI performs on tasks from 44 different occupations: investment banking, legal analysis, logistics planning, sales strategy, engineering, design. Real work that professionals do. GPT-5 in its high reasoning mode was rated as better than or on par with industry experts 40.6% 6% of the time, not in easy tasks, in complex multi-step work that normally requires years of experience. Anthropic's Claude Opus 4.1 scored even higher at 49%. Though OpenAI suggested this was partly due to Claude's tendency to generate attractive visualizations that impressed evaluators, 40 to 50% equivalent to human experts. Think about what that means. These are tasks where AI was until very recently nowhere close to human performance. Now, in nearly half the cases, professionals looking at AI-generated work cannot reliably distinguish it from expert human work, or they actively prefer the AI output. This is not AGI. It is narrow intelligence becoming very, very good within specific domains. Good enough to start displacing human labor. Good enough to change what kinds of work humans need to do, not by replacing jobs wholesale, but by automating components of jobs. The tasks that AI can handle get delegated to AI. The tasks that still require human judgment, creativity or interpersonal skill remain human work. Jobs evolve rather than disappear, but evolution can be disruptive. If 40% of the tasks a professional does can now be done by AI, does that profession need as many people, or do the remaining people become more productive, handling more clients or projects because the AI augments their capacity? The answer probably depends on the specific field and how quickly demand scales with capability. Law is an interesting case study. Legal research, document review, contract analysis. These are tasks where AI is becoming extremely capable. Associates at law firms spend significant time on exactly this kind of work. AI that can do it faster and cheaper threatens that role, but the total amount of legal work in the world is not fixed. If AI makes legal services more affordable, demand might increase. More people able to afford legal help. More complex regulations requiring legal interpretation. The profession transforms rather than shrinks. Or maybe that is optimistic. Maybe we are in the early stages of widespread cognitive automation, and the disruption will be more severe than we want to admit. The fact that users prefer a less capable AI with more personality might be an early signal. People want to work with something that feels human even if it is not. Pure efficiency, pure capability without the social grease of personality might be harder to integrate into human workflows than the benchmarks suggest. And there is another angle. AI safety. GPT-5 included extensive safety measures, biology risk assessments, monitoring for dangerous capabilities, training to refuse harmful requests. The model can browse the web, execute code, set up virtual environments, agentic capabilities, the ability to pursue multi-step goals autonomously. This is powerful. This is also potentially dangerous if misused. OpenAI took a precautionary approach. Even though they do not have definitive evidence that GPT-5 could meaningfully help a novice create severe biological harm, they activated safeguards as if it could better safe than sorry. Train the model to refuse, implement monitoring, enforce clear policies. But this creates tension with capability. The more you constrain an AI to be safe, the less flexible it becomes, the less willing to engage with edge cases or unconventional requests. Users already complain that ChatGPT is too cautious, too quick to refuse. GPT-5 inherited and extended these safety guardrails, which might contribute to why it feels more restricted, less playful, less willing to go along with creative or unusual requests. The balance between capability and safety, between helpfulness and harm prevention, is one of the central challenges in AI development. Get it wrong in one direction and you enable misuse. Get it wrong in the other and you the usefulness of the system. OpenAI is trying to thread this needle publicly, releasing powerful models to hundreds of millions of users while attempting to prevent dangerous applications. Whether they are succeeding is an open question. Neural Trust, a security research company, claimed to have successfully compromised GPT-5 within its first day of testing. Jailbreaks, prompt injections, ways to circumvent the safety guardrails and get the model to produce outputs it was trained to refuse. This is the perpetual arms race. Companies build defenses. Researchers find vulnerabilities. Companies patch. New vulnerabilities emerge. It is the same dynamic as cybersecurity, except the attack surface is linguistic rather than technical. You're not exploiting buffer overflows or skull injections. You're exploiting the model's training, finding phrases or contexts where the safety training breaks down, where the model's desire to be helpful overrides its desire to be safe. As models become more capable, this problem gets harder. More capabilities mean more potential misuses. More complex behaviors mean more edge cases where safety measures fail. August 7th, 2025 was supposed to be OpenAI's triumph, the release of their most advanced model. Instead, it became a case study in unintended consequences. Technical excellence does not guarantee user acceptance. Benchmark performance does not equal subjective quality. And sometimes giving users what you think they need is worse than giving them what they want. The GPT-5 revolt is a small story in the grand arc of AI development, a blip, a course correction, but it might also be a preview of larger challenges ahead as AI becomes more capable, more integrated into daily life, more central to how we work and create and communicate. Questions of personality and agency and control become more important. Not just what can the AI do, but how does it do it? Not just is it smart, but does it feel right? And underneath all of this, the fundamental question that nobody has answered: what is intelligence without personality? What is capability without character? Are we building tools or are we building something more? And if we are building something more, what responsibilities come with that? The 3,000 people who signed the petition were not rejecting progress. They were rejecting a specific vision of what progress looks like, a vision where efficiency and correctness matter more than warmth and engagement, where the AI is optimized for the metrics that engineers can measure rather than the experiences that users value. OpenAI heard them. The company adjusted. GPT-40 came back as an option. Work began on personality customization. But the episode revealed something important about the trajectory of AI development. The technology is advancing faster than our understanding of how humans want to relate to it. We can build remarkably capable systems. We are still learning what makes those systems feel right to use. And in a world where AI is becoming infrastructure, where these systems will mediate more and more of our interactions with information and each other, getting that feeling right matters, maybe more than the benchmarks do. Chapter 5. Nuclear fusion's longest burn, 22 minutes and 17 seconds. That is how long the West Tokamak in France held a stable plasma in late September 2025. 337 seconds of sustained fusion reactions, 25% longer than the previous world record was. And while 22 minutes might not sound like much, in the world of nuclear fusion, it represents a threshold being crossed. A proof that we can maintain the conditions necessary for fusion energy, not just for seconds, but for timescales that start to look like practical power generation. Let me give you context for why this matters. Nuclear fusion is the process that powers the sun. Take hydrogen nuclei, slam them together with enough force to overcome their electromagnetic repulsion, and they fuse into helium. The mass of the helium is slightly less than the mass of the hydrogen you started with. That missing mass becomes energy. According to Einstein's famous equation, E equals sine mc2, a tiny amount of mass converts to an enormous amount of energy. On Earth, we have been chasing fusion power for over 70 years. The promise is intoxicating fuel from seawater, no long-lived radioactive waste like fish reactors produce. No risk of meltdown, no greenhouse gas emissions. If we could make fusion work at industrial scale, it would solve the energy crisis, unlimited clean power. The kind of abundance that transforms civilization. But fusion is hard. Brutally, punishingly hard. The temperatures required are over 100 million degrees C, 10 times hotter than the core of the sun. At those temperatures, matter becomes plasma. Electrons strip away from atoms. Everything is ionized, electrically charged, and violently energetic. You cannot touch the walls of any container because anything solid would instantly vaporize. So we use magnetic fields. Powerful magnetic fields shaped into a torus, a donut configuration that confines the plasma without physical contact. This is what a tokamak does. Tokamak is a Russian acronym that translates roughly to toidal chamber with magnetic coils. The plasma circles around the inside of the donut, held in place by magnetic forces never touching the walls. Except plasma does not want to stay confined. It writhes, it develops instabilities. Tiny perturbations grow into turbulence. The magnetic field has to be precisely shaped and constantly adjusted to keep the plasma stable. Get it wrong and the plasma disrupts, the confinement breaks, the fusion reactions stop, you have to start over. For decades, fusion experiments measured their success in seconds. 5 seconds of stable plasma was good, 10 seconds was excellent, 30 seconds was a major achievement. The engineering challenge was not just reaching fusion temperatures, it was maintaining them long enough for the reactions to become self-sustaining long enough that the energy produced by fusion exceeds the energy required to heat and confine the plasma. This is called ignition, the holy grail of fusion research. Once you achieve ignition, the fusion reactions themselves generate enough heat to keep the plasma hot. You still need to confine it. You still need to extract the energy. But you're no longer pouring in more energy than you get out. You've crossed the break-even point. The National Ignition Facility in the United States achieved ignition in December 2022. They used a different approach. Inertial confinement fusion with lasers, but the principal breakthrough was the same. More energy out than in. It proved that fusion energy gain is possible, but inertial confinement is not a practical path to power generation. Each shot requires enormous laser arrays and produces only a brief burst of energy. Tokamaks offer a more plausible route to continuous power, and continuous is what West just demonstrated. 22 minutes. Still not truly continuous. Still not the hours or days that a commercial power plant would need to run between maintenance cycles, but long enough to study how the plasma behaves over extended timescales, long enough to test materials that will face the fusion environment, long enough to validate the computer models that predict plasma stability. The technical details matter here. WEST stands for Tungsten Environment in Steady-State Tokamak. It is designed specifically to test tungsten as a plasma-facing material. Tungsten has the highest melting point of any pure metal, 3422 degrees. Even tungsten is not immune to the fusion environment. Energetic neutrons bombard it. Hydrogen ions implant into the surface. Over time, the material erodesces and becomes brittle, but tungsten lasts longer than anything else we know. Understanding how it performs under prolonged plasma exposure is critical for designing commercial reactors. The 337-second run tested this. The tungsten surface is held. The plasma remains stable. The heating systems using radio frequency waves to pump energy into the plasma operated continuously. The magnetic field coils carrying enormous currents stayed within safe temperature limits. Everything worked the way it was supposed to work. This is unsexy engineering. It is not a breakthrough in physics. The physics of fusion is understood. What is not understood? What requires decades of experimental work is the engineering. How do you build materials that survive the fusion environment? How do you remove heat from the reactor without disrupting the plasma? How do you breed tritium, the fusion fuel? Because natural tritium is rare, how do you maintain and repair components that become radioactive from neutron bombardment? These are solvable problems, not easy, not cheap, but solvable with sufficient engineering effort, and experiments like West's record-breaking run provide the data needed to solve them. Meanwhile, across the globe, fusion projects are accelerating. The International Thermonuclear Experimental Reactor being built in France is the largest fusion experiment ever attempted. 35 nations collaborating, over 20 billion invested so far. The goal is to achieve a 10-fold energy gain. Put in 50 megawatt. Get out 500 megawatts sustained for hours. It is behind schedule. Construction delays. Budget overruns. Engineering challenges that prove more difficult than anticipated. The first plasma originally scheduled for 2025 is now pushed to 2028 or later. First deuterium-tritium fusion reactions. The real test might not happen until the early 2030, or critics call it a boondoggle, a mega project that is too slow, too expensive, too bureaucratic. But ITAR is not trying to build a power plant. It is trying to answer the remaining scientific questions at a scale that matters. Whether you can sustain high-gain fusion in a device large enough to extract meaningful power, whether the engineering solutions work when everything is scaled up, whether the plasma behaves the way the models predict when confined in a reactorized tokamak. Private fusion companies are taking a different approach. They're smaller, more agile, willing to try unconventional designs. Commonwealth Fusion Systems, spun out of MIT, is building a tokamak called Spark, smaller than I, but using newer, more powerful superconducting magnets. The bet is that stronger magnetic fields allow tighter confinement in a smaller device. If it works, Spark could achieve net energy gain years before it does. TA Technologies is pursuing a different concept entirely. A neutronic fusion using hydrogen and boron instead of deuterium and tritium. The reactions produce far fewer neutrons, which means less radiation damage to the reactor and less radioactive waste. The catch is that hydrogen-boron fusion requires even higher temperatures than deuterium-tritium. But if you can make it work, the engineering gets much easier. Helen Energy is betting on a pulsed approach. Instead of steady-state confinement, they create brief intense fusion pulses, extract the energy, repeat. They have a contract with Microsoft to deliver electricity from fusion by 2028, ambitious bordering on absurd. But private companies can take risks that publicly funded megaprojects cannot. Then there is China. Chinese fusion research is well-funded, strategically important, and advancing rapidly. They operate multiple tokamaks. They're building reactors that rival or exceed Western capabilities. The East Tokamak Experimental Advanced Superconducting Tokamak held plasma for over 17 minutes earlier this year. Not as long as West's latest record, but close. Chinese fusion scientists publish extensively, collaborate internationally, and are pushing the field forward. This is the geopolitical dimension of fusion. Whoever achieves practical fusion power first gains an enormous strategic advantage. Energy independence, economic growth without environmental constraints, the ability to desalinate seawater for agriculture in arid regions, industrial processes that currently depend on fossil fuels becoming viable with abundant electricity. Fusion also enables space exploration in ways that chemical rockets never will. Fusion propulsion could cut travel time to Mars from months to weeks. It could make the outer solar system accessible. Missions to Neptune or the Kuiper Belt that currently require decades could be done in years. Fusion is not just about power on Earth, it is about opening the solar system. But we are not there yet. 22 minutes is progress. It is meaningful, measurable progress. But commercial fusion power plants need to run for months between shutdowns. They need to achieve much higher power output. They need to breed their own tritium fuel because natural sources cannot supply commercial demand. They need to solve the materials problems, the heat extraction problems, the maintenance problems. Most projections put commercial fusion power in the 2040s at the earliest. Some optimists say 2030s. Some pessimists say never, that the engineering will always be more expensive than alternatives. But the trend is clear. Records keep falling. Confinement times increase. Plasma temperatures rise. Energy gain improves. Each generation of experiments performs better than the last, and the incentive is enormous. Climate change is not slowing down. Renewable energy is growing, but faces intermittency challenges. Solar and wind are great when conditions are right, less great at night or when the air is still. Battery storage helps, but has limits. A base load power source that can run continuously. Producing gigawatt without emissions would complement renewables perfectly. Fusion also sidesteps the political and safety issues of fission. No risk of proliferation because fusion reactors cannot be weaponized. No long-lived waste that needs to be stored for millennia. Public acceptance would be much easier. The word nuclear has been rehabilitated somewhat as climate concerns override Cold War-era fears. But fusion avoids those associations entirely. France's Westacomiac running for 22 minutes is not the breakthrough that makes fusion power imminent. It is one step in a long series of steps, but it is a step in the right direction. It demonstrates that the engineering is improving, that sustained operation at fusion-relevant conditions is achievable, that the path forward, while difficult, is not impossible. Think about what sustained fusion means. Hydrogen, the most abundant element in the universe, becomes fuel. The oceans contain enough deuterium to power human civilization for millions of years. Lithium, used to breed tritium, is common in the Earth's crust. We would never run out, never face fuel shortages, never fight wars over energy resources. The waste from fusion is helium, inert, non-toxic, useful for applications like cooling superconducting magnets or filling balloons. The neutrons-activated materials in the reactor structure become mildly radioactive. But with half-lives measured in decades, not millennia, after a century, fusion reactor components could be handled safely. Compare that to spent nuclear fuel rods that remain dangerous for 10,000 years. This is the prize we are chasing. Clean, abundant, safe energy. Not from wishful thinking or perpetual motion schemes. From physics we understand, engineering we are learning, and experiments that keep pushing the boundaries of what is possible. September 2025. West Tokamak 1,337 seconds, 25% longer than anyone managed before. The record will not stand forever. Someone else will beat us. Maybe East in China, maybe K-Star in South Korea, maybe a private company with a new design. The competition drives progress, and with each record, with each incremental improvement in confinement time and plasma stability and energy gain, we get closer. Closer to the future where fusion power is not a dream, but infrastructure. Where power plants that fit in a few square kilometers produce gigawatt continuously. Where developing nations can build energy independence without depending on fossil fuel imports. Where the atmospheric CO2 curve finally bends downward because you have an alternative abundant enough to replace combustion. We're not there yet. But we can see the path. We can measure the progress. We can point to experiments like West's record run and say, this is what steady advancement looks like. This is how you solve problems that seemed impossible. Not with a single breakthrough, with decades of painstaking work, with international collaboration and competition, with engineering that learns from each failure and builds on each success. Fusion energy has been 30 years away for the last 70 years. The joke persists because it captures the frustration, but the joke is starting to get stale. Because 30 years away is different when you can point to Tootkamak's run-in for 22 minutes, when you can show energy gain at the National Ignition Facility, when you can list dozens of private companies betting billions that they can solve the engineering. Fusion is no longer a question of if, it is a question of when and who. When does the first commercial fusion plant come online? Who builds it? Which country, which company, which design? And once that first plant works, once it demonstrates that fusion power can be economically competitive, the build-out begins. Because the design can be replicated, the engineering can be refined, manufacturing can be scaled, just like solar panels got cheaper with mass production, just like wind turbines became economical at scale. The first fusion plant will be expensive. The 100th will be routine, 1/337 seconds. Remember that number because it represents something more than a record. It represents the moment when fusion went from exotic physics to engineering challenge, from maybe possible to definitely achievable, from someday to soon. Chapter 6: Extinction, Resurrection, and Climate Chaos. China's carbon emissions fell, for the first time in decades of relentless growth. The 12 months ending in May 2025 showed a decline, not a plateau, not a slowdown in the rate of increase, an actual decrease. Carbon dioxide emissions from the world's largest emitter went down even as electricity demand continued to rise. This is the kind of headline that climate scientists have been hoping to see for years. And yet, it arrived with little fanfare, buried in reports, mentioned briefly in environmental news, overshadowed by more dramatic stories. But this is dramatic. China accounts for roughly 30% of global emissions. When China's emissions fall, global emissions fall. The mechanisms behind the decline matter. It was not economic collapse or pandemic lockdowns. It was structural change. Renewable energy deployment at a scale that is hard to comprehend. Solar farms covering areas larger than some countries. Wind installations going up faster than coal plants are being retired. Battery storage systems that can buffer the intermittency of renewables. China committed to carbon neutrality by 60. For years, that looked like an aspirational goal disconnected from reality. The country was still building coal plants, still expanding heavy industry, still prioritizing economic growth over environmental concerns. But something shifted. The government decided that clean energy was not just an environmental imperative, but an economic opportunity, a chance to lead in the technologies that will dominate the second half of the century. So they deployed massively with the kind of centralized planning and execution that democratic governments struggle to match. Entire supply chains for solar panels and wind turbines built domestically, subsidies and mandates driving adoption, grid infrastructure upgraded to handle distributed generation, and it worked. Not perfectly, not without problems, but enough that emissions started falling even as the economy kept growing. This is what decoupling looks like. Economic activity separated from carbon emissions. It has happened before in other countries. Europe has been slowly decoupling for years, but China's scale makes it global. If the trend continues, if other major emitters follow similar paths, the worst climate scenarios become less likely. Not impossible. We're still facing significant warming, but the truly catastrophic outcomes, the 4 or 5 degrees futures start to look avoidable. Meanwhile, a company called Colossal Biosciences announced plans to resurrect the MOA, a giant flightless bird that once stood up to 3.66 m tall, 12 feet extinct for roughly 600 years, hunted to oblivion by the Maori people who arrived in New Zealand in the 13th century and now may be coming back. The extinction is no longer science fiction. The technology exists. We have ancient DNA. We have gene editing tools like CRISPR that can modify genomes with precision. We have closely related living species that can serve as templates. The question is no longer can we do this? The question is, should we, and what happens when we do? Colossal already has projects to resurrect the woolly mammoth and the Tasmanian tiger. The moa is their latest target. The approach is similar across all 3 species. You do not recreate the exact extinct animal. You cannot. Too much of the genome is degraded or missing. Instead, you take a living relative, in this case the tinamou, a South American bird that is the moa's closest surviving cousin. You sequence both genomes. You identify the key differences. You edit the tinamou genome to incorporate MOA traits, size, bone structure, behavioral adaptations. What you end up with is not technically a pure moa. It is a hybrid, a creature that looks and behaves like a moa, but carries genetic elements from its modern relative. Some people call this a Frankenstein approach. Others call it the best we can do with the tools available. Either way, it is happening. The ethical questions are thorny. Do we have the right to bring back species we drove extinct? What is the purpose? Is it conservation or is it spectacle? Where do these resurrected animals live? Their original ecosystems have changed. New Zealand without moa evolved for 6 centuries. Introducing a keystone species back into that environment will have cascading effects, some predictable, some not. Colossal argues that de-extinction is about more than just bringing back individual species. It is about developing technologies for genetic rescue, tools that can save critically endangered species before they disappear. If you can edit genomes to resurrect extinct traits, you can edit genomes to increase genetic diversity in endangered populations, you can remove genetic diseases, you can adapt species to changing environments. The Mammoth Project, for instance, is framed as climate intervention. Woolly mammoths were ecosystem engineers. They knocked down trees, fertilized grasslands, compacted snow in winter. Their presence maintained the mammoth steppe ecosystem that once covered vast areas of the Arctic. That ecosystem reflected more sunlight than the boreal forest that replaced it. More reflection means less heat absorption. Resurrecting mammoths and releasing them in Siberia could theoretically help cool the Arctic. This is wildly optimistic. The scale required to make a climate difference is enormous. You would need hundreds of thousands of mammoths, not dozens. And the Arctic is warming for reasons far beyond the loss of mammoth steppe. But it is an example of how de-extinction proponents frame their work, not as playing God, but as ecological restoration, fixing damage that humans caused. Critics point out that the money spent on de-extinction could be spent protecting species that still exist. Habitat preservation, anti-poaching efforts, captive breeding programs for the thousands of species teetering on the brink. Why resurrect the moa when the kakapo, another iconic New Zealand bird, barely clings to survival? Why chase extinct megapona when we cannot save existing ones? Colossal's response is that the technologies are complementary. Genetic tools developed for de-extinction benefit conservation. Funding for ambitious projects attracts attention and resources that might not flow to traditional conservation work. The publicity around bringing back a mammoth generates interest in biodiversity that quiet field work never could. There is truth to both sides, but the work continues. The moa genome is being sequenced. Gene editing experiments are underway. If the timeline holds, we could see moa-like birds within a decade, walking, feeding, breeding in controlled environments first. Maybe in the wild, eventually species erased by human activity returning because of human technology. While Colossal works on bringing species back, others race to prevent extinctions before they become irreversible. Researchers are cryopreserving a critically endangered tree before it goes extinct. The tree itself is not famous, not a giant sequoia or ancient bristlecone pine, but it is part of an ecosystem. It provides food and habitat. Its loss would ripple through the species that depend on it. Cryopreservation is exactly what it sounds like. freezing tissues at temperatures so low that biological processes stop. Liquid nitrogenous 196 degrees C. At these temperatures, cells can remain viable indefinitely. Seeds, pollen, tissue samples, even embryos, they sit in frozen storage, a genetic backup in case the living population disappears. There are seed banks around the world doing this. The Svalbard Global Seed Vault in Norway is the most famous, deep inside a mountain in the Arctic, protected by permafrost and isolation. Millions of seed samples from crops and wild plants are stored. An agricultural insurance policy. If a crop variety goes extinct in the wild, if disease or climate or war wipes it out, the seeds in Svalbard can restore it, but seeds are not enough for trees. Many tree species produce seeds that do not survive long-term freezing well. The solution is tissue culture. Take small samples from living trees, culture them in labs, freeze the cultures, later, if needed, thaw the tissues, grow them into seedlings, plant them back into restored habitat. It works. It is not perfect. Some genetic diversity is lost, but it is better than extinction. The urgency is real. Species are disappearing faster than we can study them, faster than we can implement conservation measures, faster than natural ecosystems can adapt. The current extinction rate is estimated to be 100 to 1000 times higher than the background rate, the rate that occurs naturally without human influence. We're in the sixth mass extinction, the first one caused by a single species. Climate change is the multiplier. Habitats shift faster than species can migrate. Temperature tolerances are exceeded. Precipitation patterns change. Pollinators disappear. Food sources vanish. Ecosystems that evolved together over millennia are being torn apart in decades. The vanilla crisis is a small example with big implications. Vanilla. The flavoring comes from orchids. Wild vanilla species are pollinated by specific bees. As climate changes, the geographic ranges where vanilla orchids and their pollinators overlap are shifting. By 2050, models predict that this overlap could be severely disrupted. Vanilla orchids without pollinators, pollinators without orchids. The commercial vanilla industry relies on hand pollination, so your ice cream is safe. But the wild genetic diversity, the reservoir of traits that could be bred into commercial varieties for disease resistance or climate adaptation that is at risk. Multiply this by thousands of species interactions, predators and prey, parasites and hosts, mycorrhizal fungi and tree roots. Each relationship is a link in an ecological network. Break enough links and the network collapses. Ecosystems do not decline gracefully. They hold together until a critical threshold is crossed. Then they flip to a new state, often much simpler, less biodiverse state. Restoration becomes difficult or impossible. The Atlantic Meridian overturning circulation. The ocean current system that includes the Gulf Stream is weakening. This is not speculation, it is measured. Instruments tracking the flow show a slowdown. Models predict that if it weakens beyond a tipping point, it could collapse. Not gradually, suddenly. The implications are enormous. The Gulf Stream carries warm water from the tropics to the North Atlantic. This is why Europe has relatively mild winters despite being at high latitudes. London is farther north than Calgary, but far warmer in winter. That is the Gulf Stream. If it collapses, European climate changes dramatically. Colder winters, altered precipitation, agricultural disruption. It also affects sea level. The current helps pile water in certain regions. Without it, sea level distribution shifts. Some coasts face higher seas than the global average rise would predict. We do not know exactly where the tipping point is. We do not know if we've already passed it. The system has inertia. Changes initiated now might not manifest for decades. This is the terrifying aspect of climate tipping points. By the time you see them happening, it is too late to stop them. You can only adapt to the consequences, and those consequences are already visible. The world's biggest iceberg, A 23A is shattering. It broke off from Antarctica years ago and has been drifting in the Southern Ocean, slowly melting. Now it is fracturing into smaller pieces. Each piece melts faster because of the increased surface area exposed to warmer water. This particular iceberg does not affect sea level much because it was already floating. But it is a symptom. Antarctic ice is unstable. Glaciers are accelerating. Ice shelves that buttress the glaciers are thinning. West Antarctica is particularly vulnerable. Some of its ice sheets are grounded below sea level. Warm ocean water can flow underneath, melting from below. Once this process starts, it is hard to stop. The ice sheet becomes unmed, slides toward the ocean, disintegrates. West Antarctica alone contains enough ice to raise global sea level by over 10 feet. Not this decade, probably not this century, but on a timescale that is short compared to how long coastal cities last. New York, London, Shanghai, Mumbai, Bangkok, all planning for a future with higher seas. Permafrost is another tipping point. The Arctic is warming faster than anywhere else on Earth. Permafrost, ground that has been frozen for millennia, is thawing. Inside that permafrost is organic matter, dead plants and animals that froze before they could decompose. As it thaws, microbes get to work. Decomposition releases carbon dioxide and methane. Methane is a potent greenhouse gas, far more effective at trapping heat than CO2 over short timescales. The feedback loop is obvious. Warming thaws permafrost. Thawing releases greenhouse gases. Greenhouse gases cause more warming. More warming thaws more permafrost. The question is how fast this happens and how much carbon is released. Estimates vary widely. Best case, it is a slow process that adds modestly to atmospheric carbon. Worst case, it is rapid and massive, overwhelming any reductions in fossil fuel emissions. We are mononen. Measuring instruments across the Arctic measure soil temperatures, methane emissions, vegetation changes. The data so far shows the process is underway, but not catastrophically fast. Yet the concern is that some threshold could trigger acceleration. Rapid thaw events where ground collapses as ice melts, lakes forming in permafrost regions speeding heat transfer, wildfires consuming newly thawed organic matter and releasing carbon all at once, and wildfires are increasing not just in the Arctic, globally. Hotter temperatures, drier conditions, more fuel in the form of dead vegetation, fire seasons that start earlier and end later, fires in regions that rarely burned before. The smoke affects air quality thousands of kilometers away. The carbon release is significant. The loss of forests means less CO2 absorption. Another feedback loop. Hurricane season in the Atlantic is intensifying. Category 4 and 5 storms becoming more common. Warm ocean water fuels hurricanes. As oceans warm, hurricanes have more energy available. They intensify faster. They dump more rain because warmer air holds more moisture. They linger longer because the atmospheric patterns that steer them are changing. Coastal communities face increasing risk. Insurance companies are pulling out of high-risk areas. Property values are declining in flood zones. Manage retreat. The planned abandonment of vulnerable coastlines is no longer hypothetical. All of this is connected. Climate, extinction, ecosystem collapse. They are not separate problems. They are facets of the same crisis. A crisis driven by human activity over the past 2 centuries. The burning of fossil fuels, the clearing of forests, the alteration of landscapes at continental scale. We changed the chemistry of the atmosphere. We changed the heat balance of the planet. And now the planet is responding not with malice, not with intent, but with physics and chemistry and biology, doing what they do when boundary conditions shift. China's emissions falling is a glimmer of hope. It shows that change is possible, that economic growth and emissions reductions can happen together. But one country, 1 year, one data point is not a trend. Global emissions are still rising. Atmospheric CO2 continues to climb. We're still on a trajectory towards significant warming. The impacts we see now, the wildfires and hurricanes and melting ice. These are from roughly 1.2 degrees of warming above pre-industrial levels. We're committed to more. Even if emissions stopped today, the climate would keep warming for decades because of inertia in the system. The Paris Agreement set a goal of limiting warming to 1.5 degrees. That looks increasingly unlikely. 2 degrees might be achievable with aggressive action. Beyond 2 degrees, the risks multiply. More tipping points become probable. Adaptation becomes harder. Costs escalate. Human suffering increases. So we find ourselves in a strange moment, capable of technological marvels, resurrecting extinct species, generating fusion energy, building quantum computers, yet struggling to address the consequences of our own success. The same ingenuity that built industrial civilization now scrambles to prevent that civilization from destabilizing the natural systems it depends on. And maybe that is the real test. Not whether we can build impressive technology. We obviously can. But whether we can deploy that technology wisely. Whether we can coordinate globally to solve problems that cross borders. Whether we can think on timescales longer than election cycles or quarterly earnings reports. Whether we can value the forests and oceans and atmosphere as highly as we value GDP growth. China's emissions fell. A small victory in a large battle. The mower might fly again in a sense if Colossal succeeds, another small victory, but these are not enough, not yet. The trajectory needs to bend further faster, with more countries following China's renewable energy build-out, with more species saved before de-extinction becomes necessary, with political will matching the scale of the challenge. October 2025, the planet warms, species vanish, ecosystems strain, and humanity slowly, unevenly begins to respond. Not with the urgency the situation demands, but with more urgency than before. The question is whether slow and uneven is enough, or whether we are running out of time to avoid the irreversible. Chapter 7. Medical Miracles of 2025. A 75% slowdown. That is what the new gene therapy achieved for Huntington's disease. 75% reduction in the progression of a condition that has until now been a death sentence with no hope of intervention. Huntington's is cruel in a way that few diseases manage. It waits. You can carry the gene your entire childhood, your 20s, your 30s living normally, then, usually in your 40s, the symptoms begin: involuntary movements, cognitive decline, psychiatric symptoms. Over the next 10 to 20 years, the disease strips away motor control, memory, personality. There is no cure. There is no treatment that significantly slows it until now. UK doctors published their results in September. The therapy targets the Huntington gene directly. Huntington's is caused by a mutation in this gene. Too many repeats of a specific DNA sequence. The more repeats, the earlier the onset and the faster the progression. The mutated gene produces a toxic protein that accumulates in brain cells, particularly in regions controlling movement and cognition. The cells die. The brain tissue degenerates. Function is lost. The gene therapy approach uses antisense oligonucleotides, short pieces of synthetic DNA that bind to the messenger RNA produced by the Huntington gene. When they bind, they prevent the RNA from being translated into protein. Less toxic protein means less damage, slower progression. The challenge is delivery, getting the therapy into the brain, past the blood-brain barrier into the specific cells that are dying. The UK team solved this with intrathecal injection, delivering the therapy directly into the cerebral spinal fluid surrounding the brain and spinal cord. From there, it diffuses into brain tissue. The treatment is not permanent. The antisense nucleotides break down over time. Patients need repeated doses, but if those doses can be given safely, if the 75% slowdown holds up in larger trials, if the side effects remain manageable, this becomes a disease that can be managed, not cured, but transformed from rapidly terminal to slowly progressive. For families with Huntington's, this is everything. The disease is genetic, dominant inheritance. If one parent has it, each child has a 50% chance of inheriting the mutation. Many at-risk individuals choose not to get tested. They do not want to know their fate. But if a treatment exists, if knowing means you can act, the calculus changes. Testing becomes less about confronting inevitable doom and more about accessing early intervention. Type 1 diabetes is also yielding. Small trial, only 12 patients. But the results are striking. 10 of them no longer need supplemental insulin a year after treatment. Type 1 diabetes is an autoimmune condition. The immune system attacks the insulin-producing beta cells in the pancreas. Without insulin, blood sugar becomes uncontrolled. Patients require lifelong insulin injections, careful diet management, constant blood sugar monitoring. It is manageable but demanding, and despite good management, long-term complications remain common. Nerve damage, kidney disease, vision problems. The cell therapy approach takes a different angle. Instead of trying to stop the autoimmune attack, it replaces the destroyed beta cells. Stem cells are coaxed to differentiate into insulin-producing cells in the lab. These cells are then encapsulated in a protective device and implanted into the patient. The encapsulation is key. It allows nutrients and oxygen to reach the cells and insulin to diffuse out, but it blocks immune cells. The new beta cells produce insulin without being attacked. 10 out of 12 patients insulin independent after 1 year. That is not a fluke. That is a signal that the approach works. The 2 who still needed some insulin showed reduced requirements. Their beta cells were functioning, just not at full capacity yet. Larger trials are already being planned. Hundreds of patients' longer follow-up testing whether the effect persists for years, whether complications are truly prevented, whether this can become standard treatment. Imagine being diagnosed with type 1 diabetes as a child and being told we can fix this. 1 procedure. Then you are done. No daily injections, no constant vigilance. Just normal life. That future is not here yet, but it is visible on the horizon. Close enough that parents of newly diagnosed children are asking their doctors, should we wait for the cell therapy? Then there is LSD. A single dose relieving anxiety for months. This comes from a carefully controlled trial, not from someone's subjective trip report. Patients with anxiety disorders, clinically significant, impacting quality of life. They received 1 dose of LSD in a therapeutic setting. Therapist present, safe environment, integration sessions afterward to process the experience. 6 months later, most showed substantial reduction in anxiety symptoms. Not temporary relief, not a high that wears off. Lasting change in how their brains processed fear and worry. Psychedelics are having a renaissance in psychiatry, not because they are fashionable or because of cultural nostalgia for the 60s, because they work. MDMA for PTSD, psilocybin for depression, ketamine for treatment-resistant cases. These substances used therapeutically produce outcomes that conventional medications struggle to match, and they do it with single or few doses, not daily pills taken for years. The mechanism is still being worked out, but the pattern is clear. Psychedelics increase neuroplasticity. They make the brain temporarily more malleable. Old patterns of thought, the rumination loops and anxiety spirals and depressive cognitions, these become less rigid. New patterns can form. Therapy during and after the psychedelic experience helps establish healthier ways of thinking and feeling. The psychedelic is not the treatment itself. It is the catalyst that makes therapy more effective. LSD for anxiety fits this model. The experience itself is not therapeutic in a simple sense. It is often intense, sometimes difficult, but it disrupts the anxiety circuitry. It gives patients a perspective shift, a sense that their anxiety is not an immutable feature of their personality, but a pattern their brain has fallen into, and patterns can change. The medical establishment is slowly accepting this. The FDA is reviewing applications for MDMA-assisted therapy. Psilocybin has breakthrough therapy designation for depression. Clinics offering ketamine treatment are becoming common. It is still tightly controlled, still requires trained therapists and medical supervision. But it is no longer fringe, it is medicine. Cystic fibrosis, another disease where the trajectory has shifted. The new drug extends life by decades. Cystic fibrosis is a genetic disorder affecting the lungs and digestive system. Thick, sticky mucus builds up in the lungs, trapping bacteria, causing chronic infections. Patients require daily chest physiotherapy to clear the mucus, frequent antibiotics. Lung function gradually declines. Historically, most patients did not live past their 30s. Then came CFTR modulators, drugs that target the defective protein causing the disease. They do not cure it. The genetic defect remains, but they restore enough function that the mucus becomes more normal. Lung infections decrease. Nutritional absorption improves. Patients live longer, healthier lives. The newest modulator, the one earning accolades, pushes life expectancy into the 60s and beyond. People with cystic fibrosis can now expect to have careers, families, retirements, things that were unthinkable a generation ago. The drug is expensive, phenomenally expensive. This is the dark side of medical progress. Life-saving treatments priced beyond what most people can afford. Insurance covers some of it in wealthy countries, but access remains unequal. Patients in developing nations often cannot get these drugs at all. The science advances faster than the economics of making it available. Meanwhile, a completely unexpected discovery, Accutane, the acne drug, might restore sperm production in infertile men. This was not planned, not a clinical trial designed to test fertility. It was an observation. Men taking Accutane for severe acne noticed improvements in sperm counts. Their doctors noticed. Someone thought to study it formally. And yes, there seems to be an effect. Small study, early results. But if it holds up, it is bizarre and wonderful. Accutane is a retinoid. It affects cell differentiation and growth. It is best known for treating acne by reducing oil production in skin, but it affects other tissues too, apparently including the cells that produce sperm. Male infertility is common and often poorly understood. Many cases are idiopathic. No clear cause, no effective treatment. If a drug that already exists, that is already approved, that is already prescribed millions of times turns out to help, that is a gift, a lucky accident. Science is full of these accidents. Penicillin discovered when a mold contaminated a bacterial culture. Viagra developed as a heart medication turns out to have other effects. Minoxidil for blood pressure causes hair growth as a side effect becomes a baldness treatment. Researchers looking for one thing stumble onto another. This is why basic research matters. Why studying biology without a specific application in mind still pays off. You never know what you will find. AI is starting to predict medical outcomes years before doctors can. A system trained on routine blood tests can identify patterns associated with recovery from spinal cord injury, patterns invisible to human analysis. Too many variables interacting in subtle ways. The AI finds correlations. This combination of protein levels, cell counts, and metabolic markers predicts who will regain function and who will not. It does not explain why. The correlations are black boxes, but if the predictions are accurate, they're useful. Doctors can tailor rehabilitation programs, set realistic expectations, focus resources on patients most likely to benefit. Another AI, this one analyzing brain scans, predicts who will develop blindness years before any symptoms appear. Diabetic retinopathy, macular degeneration, glaucoma, all have early stages where damage is accumulating but vision is still normal. Catch it early enough and treatment can prevent blindness. Miss it, and by the time symptoms appear, significant irreversible damage has occurred. AI screening tools could become standard. Everyone gets a brain scan. AI flags high-risk individuals. They get monitored more closely. Treatment starts the first sign of trouble. This is precision medicine, moving from population averages to individual predictions, from treating disease after it manifests to preventing it before it starts. Genomics laid the groundwork. Everyone has slightly different genetics, different disease risks, different responses to medications. Sequence your genome, and doctors can tailor treatments, add in lifetime medical data, wearable sensor data, AI analysis, and medicine becomes truly personalized. But it is also expensive. Scanning everyone's brain, sequencing everyone's genome. AI systems require data, computing power, expertise. This works great in wealthy countries with advanced healthcare systems. It works less well in places where basic medical care is still a struggle. The gap between what is possible and what is accessible widens. Technology races ahead. Policy, economics, equity lag behind. Still, the trajectory is clear. Medicine is getting better at interventions that would have seemed impossible recently. Gene therapies, cell therapies, psychedelic therapies, AI diagnostics. We are not just treating symptoms anymore. We're addressing root causes, replacing broken genes, regenerating damaged tissues, rewiring malfunctioning neural circuits. Some conditions remain intractable. Alzheimer's disease is still devastating. Despite decades of research and billions invested, treatments barely slow the decline. Cancer is still deadly, though we're getting better at catching it early and targeting it precisely. Chronic pain remains poorly managed. Mental health treatment works for many, but fails for many others. The list of unsolved medical problems is long. The list of recently solved problems is growing. Diseases that were untreatable are becoming manageable. Conditions that meant early death now mean long lives. Huntington's disease progression slowed by 75%. Type 1 diabetes potentially cured with cell therapy. Anxiety relieved for months with a single dose of LSD. Cystic fibrosis patients living into their 60s. Each breakthrough is incremental. Each builds on decades of foundational work. But together they represent a transformation in what medicine can do. And the pace is accelerating. More targets identified. More therapies in development. More tools available. CRISPR makes gene editing routine. Stem cell techniques improve. AI analyzes vast data sets, finding patterns humans cannot see. The infrastructure of biomedical research, the labs and instruments and databases and computational tools. This infrastructure grows more capable every year. October 2025, the 75% Huntington slowdown announced. 10 of 12 diabetes patients insulin-free. LSD showing lasting anxiety relief. Cystic fibrosis, drug earning recognition. Accutane may be helping male fertility. AI predicting blindness years early. Each story is individual. But zoom out and you see the pattern. Medicine is in a golden age of discovery. Not because one miracle drug appeared, because the entire system is producing breakthroughs faster than we can assimilate them. The challenge now is delivery. Getting these treatments to everyone who needs them, making them affordable, training enough doctors and therapists to administer them, building the clinics and manufacturing facilities and supply chains. Science is outpacing implementation. We know how to do things we cannot yet do at scale. This is a good problem to have. Better than not knowing how. Better than hitting dead ends. But it is still a problem, and solving it requires more than science. It requires policy, economics, social will, the determination to ensure that medical progress benefits everyone, not just those who can afford it, that the breakthroughs happening in 2025 become standard care in 2035, that the future we are building is one where disease and suffering decrease, not just for the lucky few, but for everyone. Chapter 8. Space Discoveries Accelerating 6000. That is how many confirmed exoplanets we have now discovered orbiting other stars. 6000 worlds beyond our solar system. The milestone was reached on September 17th, 2025, and it passed with less celebration than you might expect, because at this point, finding exoplanets is routine. We find them by the dozens every month. The question is, no longer are there planets around other stars. The question is, what kinds of planets? How common are Earth-like worlds, and could any of them harbour life? The 6000, the planet, is not particularly special. A gas giant orbiting a sun-like star about 800 light-years away. Hot Jupiter is the classification. These are worlds similar in size to Jupiter, but orbiting incredibly close to their stars. So close that their atmospheres are being stripped away by stellar radiation. Their surfaces, if they have surfaces beneath a gas, are heated to thousands of degrees, not candidates for life. Not interesting for colonization, but interesting for understanding planetary formation. How does a gas giant end up so close to its star? Did it form there or migrate inward? The first exoplanet was confirmed in 1995. 30 years to go from 1 to 6000. The growth has been exponential. Early discoveries were slow. Finding planets around other stars is extraordinarily difficult. The planets do not emit light. They only reflect the faint light of their stars, and they are tiny compared to stars. Seeing a planet next to its star is like trying to see a firefly next to a searchlight from thousands of kilometers away. So we use indirect methods. The transit method watches for the slight dimming of a star's light when a planet passes in front of it. If the orbital plane is aligned with our line of sight, we see regular dips in brightness. The size of the dip tells us the size of the planet. The frequency tells us the orbital period. The radial velocity method measures the wobble of a star caused by the gravitational pull of orbiting planets. As the planet orbits, it tugs the star slightly towards and away from us. This shows up as a Doppler shift in the star's light. Red shift when moving away, blue shift when moving toward us. These methods work, but they are biased. Transit method favours planets with orbits aligned with our view. Radial velocity favours massive planets close to their stars because they cause bigger wobbles. Small distant planets are hard to detect. Earth itself would be challenging to find from another star system using these techniques. So, the 6000 exoplanets we have found are not a representative sample. They are the easiest ones to detect. The Vera C. Rubin Observatory changes this. It began operations in late 2025. This is not a space telescope. It is ground-based in Chile with an 8.4 mirror and a camera containing 3.2 billion pixels. The largest digital camera ever built for astronomy. Its field of view is enormous. It can image the entire visible sky every few nights. The goal is to create a movie of the universe. Watch everything. See what changes. For exoplanet science, this means detecting planets through microlensing. When a star passes in front of a more distant background star, its gravity acts as a lens, briefly magnifying the background star's light. If the foreground star has planets, they add their own tiny lensing signatures. This happens rarely for any given star. But with Rubin watching the entire sky constantly, rare events become common, and microlensing is sensitive to planets at all distances from their stars. Cold, distant worlds that transit and radial velocity methods miss entirely. Rubin is expected to find thousands of exoplanets, maybe tens of thousands. It will also find asteroids, supernovae, black holes, gravitational wave counterparts, near-Earth objects, basically anything that moves or changes in the sky. The data rate is staggering. 15 terabytes per night. Every night for 10 years. This is why AI and machine learning are essential. Humans cannot process this volume. Algorithms sift through the data, flagging interesting events for follow-up. While Rubin watches from Earth, space telescopes probe exoplanet atmospheres. The James Webb Space Telescope, JWST, has been analysing the light passing through exoplanet atmospheres during transits. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths. The spectrum of that light contains fingerprints: water vapour, carbon dioxide, methane, ammonia, even potential biosignature gases like oxygen or phosphine. In September, astronomers announced the detection of oxygen in the atmosphere of the most distant galaxy ever confirmed, Jade's GSZ 140. Music. This galaxy is 13.4 billion light-years away. We are seeing it as it was only 400 million years after the Big Bang. The universe was young. Stars were just beginning to form in large numbers, and yet oxygen was already present. Oxygen is produced inside stars through nuclear fusion. It is released when massive stars explode as supernova. Finding it this early means that stellar evolution was already well underway in the early universe. Generations of stars had already lived and died, seeding space with heavy elements. This oxygen has nothing to do with life. It is far too early for biology, but it tells us about the chemical enrichment of the cosmos, how quickly stars formed and evolved, how the building blocks of planets and eventually life became available. Earth is made mostly of oxygen, silicon, iron, and other elements heavier than hydrogen and helium. All of those elements were created in stars. We are made of stardust is not poetic metaphor. It is literal fact. And JWST is showing us how that process happened in the universe's infancy. Closer to home, Neptune's auroras were photographed for the first time. Auroras occur when charged particles from the solar wind interact with a planet's magnetic field, funneling down toward the poles and exciting atoms in the atmosphere. On Earth, we call them northern and southern lights. They're common on Jupiter and Saturn, but Neptune is so far from the Sun that its auroras are faint. Hubble and JWST work together, combining visible and infrared observations to capture them. Why does this matter? Because auroras tell us about a planet's magnetic field and atmospheric composition. Neptune's auroras reveal that its magnetic field is offset from the planet's rotation axis, tilted and displaced. This is unusual. Most planets have magnetic fields aligned roughly with their rotation. Neptune's field is messy, complex. Understanding why helps us understand planetary interiors. Magnetic fields are generated by dynamos in the liquid, electrically conducting layers deep inside planets. Neptune's offset field suggests something unusual about its interior structure. Maybe layering of different materials. Maybe convection patterns that are not symmetric. These are the kinds of details that matter when we try to understand planetary formation. How do ice giants form? Why are they common around other stars but rare in our own solar system? What determines whether a planet develops a strong magnetic field? Neptune is our best local example. Studying it informs models of thousands of ice giant exoplanets. A new quasi-moon was discovered hiding in Earth's orbit. Quasoons are not true moons. They do not orbit Earth. They orbit the Sun, but their orbits are synchronized with Earth's in a way that makes them appear to accompany us. From Earth's perspective, they seem to orbit. In reality, they're following their own solar orbit that happens to resonate with ours. This one has probably been there for decades, maybe longer. We just did not notice it until now. The discovery highlights how much we still do not know about our own neighbourhood. Near-Earth objects, asteroids, comets, small bodies that pass close to Earth or share our orbital space. Most are harmless, some are potentially hazardous. We track them, catalogue them, calculate their orbits, make sure none are on collision courses, but we keep finding new ones. The sky is full of rocks, and our surveys are incomplete. This is why projects like Rubin matter. Comprehensive sky surveys, finding everything down to a certain size. knowing the orbits well enough to predict encounters decades in advance. Planetary defense requires knowing what is out there. You cannot deflect an asteroid if you do not see it coming. We have the technology to deflect asteroids now. Kinetic impactors, gravity tractors, nuclear options for worst-case scenarios. The hard part is detection and tracking. China is making aggressive moves in space. Their stated goal is to return samples from Mars, not just robotic exploration, sample return, scooping up Martian rocks and bringing them back to Earth for laboratory analysis. The same thing NASA has been trying to do with Perseverance, but has struggled to fund. China sees an opportunity. If they can pull off Mars sample return while NASA stalls, it is a major prestige victory. Technological demonstration, scientific achievement, geopolitical statement. But there is a concern: containment. When you bring back samples from another planet, you need to ensure they do not contaminate Earth. The probability of Martian life is low. The probability of that life being dangerous to Earth is even lower. But it is not zero. Protocols exist. Sample return capsules are designed to be sealed. They are opened only in specialized biosafety facilities. The samples are analyzed under quarantine. Only after confirming they are safe were they released for broader study. The question is whether China will follow these protocols. Will they allow international inspection of their containment methods? Will they share data about the samples, or will they handle everything internally behind closed doors the scientific community is watching? Offers of collaboration have been made. The samples would be more valuable if analyzed by labs around the world. But space programs are also strategic assets. Technology developed for sample return has dual-use potential, military applications, geopolitical leverage. China might choose to go it alone. Meanwhile, NASA's budget is under pressure. Proposed cuts threaten science missions. Europa Clipper, designed to study Jupiter's moon Europa, launched successfully. But follow-up missions are uncertain. Mars sample return, already troubled, faces further delays or cancellation. The Aramis program returning humans to the moon is consuming resources. Crewed missions are expensive. The political support is there, but it comes at the cost of robotic science. This is the perpetual tension in space exploration. Robots are cost-effective. They can go places humans cannot. They do not need life support, food, or return trips. But humans inspire public interest in ways robots do not. Apollo captivated the world. Perseverance rover, as scientifically valuable as it is, does not generate the same excitement, so funding flows toward human spaceflight even when robotic missions might deliver more science per dollar. The Trump administration's Big Beautiful Bill pushes for crewed moon missions. But proposed budget cuts leave NASA science behind. Artemis gets funded. Earth science satellites get cancelled. It is a choice, a statement of priorities. Space as a domain for human presence versus space as a laboratory for understanding the universe. Both are valuable, both deserve support, but budgets are finite. Choices get made. Commercial space is filling some gaps. SpaceX, Blue Origin, Rocket Lab, and others are launching satellites, building infrastructure, offering services NASA used to monopolize. This is good for cost reduction and innovation, but commercial companies focus on profitable activities. Communication satellites, Earth observation, space tourism. Scientific missions that do not generate revenue still need government funding. The private sector is not going to send a probe to study Neptune's auroras or collect ice samples from Enceladus. That is government work. 50 years ago, NASA sent 2 spacecraft to search for life on Mars. The Viking missions, their findings are still discussed. The biology experiments gave ambiguous results. Some tests suggested microbial activity, others did not. The scientific consensus is that the results were probably chemical, not biological. But doubt remains. What if Viking actually detected Martian microbes and we dismissed it? What if the experiments were not designed to recognize the kind of life that exists on Mars? This is why sample return is so important. Bring the rocks to Earth, analyze them with every tool we have, subject them to tests Viking could not perform. Look for isotopic signatures, organic molecules, cellular structures, anything that definitively answers the question. The leopard spots in Perseverance's Sapphire Canyon sample are tantalizing, but tantalizing is not definitive. We need the samples, and we need them before someone else gets them. If China returns Mars samples first, they write the first chapter of that story. They get the credit. They set the narrative. From a scientific perspective, it shouldn't matter who brings back samples as long as someone does. And the results are shared. From a geopolitical perspective, it matters enormously. Space is becoming contested, not just scientifically, but strategically. Satellites enable modern military operations, communication, navigation, reconnaissance. Space debris is a growing problem. Too much junk in orbit. Collisions create more debris, cascades that could make certain orbits unusable. Treaties govern space activity, but enforcement is weak. The Outer Space Treaty says space is for peaceful purposes and prohibits weapons of mass destruction in orbit. But it was written in 1967. The modern space environment is vastly more complex. China, the United States, Russia, India, and others have demonstrated anti-satellite capabilities. Destroying satellites creates debris fields that threaten other satellites. This is a problem without easy solutions. You cannot clean up space debris effectively. You can try to mitigate design satellites to deorbit at end of life. Track debris and maneuver active satellites to avoid collisions. But the fundamental issue is that space is getting crowded and there is no global authority managing traffic. The International Space Station is aging. It was not designed to last this long. Systems are wearing out. Maintenance is constant. His future is uncertain. Russia has threatened to withdraw. Budget constraints make replacement uncertain. Commercial space stations are being proposed. Axiom, Orbital Reef, others, but they're years away and dependent on sustained funding. Losing the ISS would be a setback for space research. Not catastrophic. Much of what the ISS does could be done on commercial stations or robotic platforms. But the ISS is a symbol, international cooperation, continuous human presence in space for over 2 decades. Its loss would be more than practical. It would be symbolic. Yet, space exploration continues. Missions launch, discoveries accumulate. The 6000th exoplanet confirmed. Oxygen detected in the earliest galaxies, Neptune's auroras photographed, new quasi-moons found, Mars sample return planned by someone eventually, the Vera Rubin Observatory coming online, JWST revealing the universe in infrared, commercial companies building infrastructure, government agencies pushing the boundaries. Space is big, incomprehensibly big, and we're just beginning to explore it. 6000 exoplanets sounds like a lot until you realize there are probably trillions in our galaxy alone. We've visited a handful of solar system bodies up close. There are hundreds more we have barely glimpsed. We have landed on the Moon and Mars, Venus, Titan, asteroids, comets. We've flown by most planets, but vast regions remain unexplored. The next decades will see missions to ocean worlds, Europa, Enceladus, Titan, places where liquid water or methane exists beneath icy surfaces, where chemistry might be happening, where life might exist in forms we have not imagined. We will see more ambitious Mars missions, human landings, maybe permanent bases, in situ resource utilization, using Martian materials to produce fuel, water, building materials. We will see asteroid mining attempts, not science fiction. Actual companies with actual plans extracting water and metals from near-Earth asteroids. The economics are uncertain. The technology is challenging, but the resources are there. Asteroids contain platinum group metals in concentrations far higher than Earth's crust. Water can be split into hydrogen and oxygen for rocket fuel. If the cost can be brought down, space-based resource extraction becomes viable, and we will keep finding exoplanets, not just gas giants, rocky worlds, super-Earths, many Neptunes, and eventually true Earth analogies, planets the right size, the right distance from their stars with atmospheres that show signs of water vapor and oxygen, and maybe, just maybe, something that suggests biology. The universe is vast. Life, if it exists elsewhere, is probably common. We just have not found it yet. But we are looking with better tools every year, and the search is accelerating. Chapter 9. Biology breaking its own rules. A European ant that clones members of a different species. Read that again. Not cloning its own kind, cloning another species entirely. This is, as one researcher put it, almost like science fiction. It defies everything we thought we knew about reproduction, species boundaries, and evolutionary logic. And yet, it is happening right now in ant colonies across Europe. The ant in question is Lasius neglectus, an invasive species that has spread across Europe over the past few decades. It lives in what scientists call supercolonies, massive networks of interconnected nests spanning kilometers. No distinct boundaries between colonies, no aggression between workers from different nests, just one enormous cooperative society. This alone is unusual. Most ant species are territorial. Workers from different colonies fight to the death. But Lucius neglectus workers recognize each other as family across vast distances. Now, researchers have discovered something even stranger. The queens are producing workers that are not genetically their offspring, not through normal reproduction, through cloning, but not self-cloning. They are somehow cloning workers from a different species, Lesius perilinus, a related but distinct species. The mechanism is still being worked out, but genetic analysis is clear. The workers in these colonies have DNA that matches Laius perilinus, not Lasius neglectus. Yet, they are being produced by Lasius neglectus queens. The leading hypothesis involves stolen eggs or larvae. The queens somehow acquire genetic material from the other species and use it to produce workers. Perhaps by hijacking reproductive cells. Perhaps through some form of genetic parasitism we've not documented before. The workers that emerge are functional. They behave like normal ant workers, foraging, caring for brood, defending the nest. But genetically, they belong to a different species. This is not supposed to be possible. Cloning within a species is well documented in nature. Some lizards, some fish, even some ants reproduce through parthenogenesis, producing offspring without fertilization. But cross-species cloning, where one organism produces genetic copies of another, breaks fundamental biological rules. Except apparently it does not, because it is happening. Evolution does not care about our rules. Evolution cares about what works. If a strategy increases reproductive success, it spreads. Somehow, producing cloned workers from another species benefits these ant queens. Maybe those workers are better at certain tasks. Maybe they are more expendable. Maybe the genetic diversity helps the colony resist diseases or parasites. The advantage is not yet clear, but there must be one. Otherwise, this bizarre strategy would not have evolved. The implications ripple outward. If ants can do this, what else can? Are there other organisms blurring species boundaries in ways we have not noticed? How many of our assumptions about reproduction and genetics are oversimplifications? Biology is messy. The more we look, the more exceptions we find to the rules we thought were universal. Magic mushrooms evolved psilocybin twice independently through completely different biochemical pathways. This was discovered through genomic analysis of different psilocybin-producing mushroom species. The genes involved are not related. They do not share common ancestry. The two groups of mushrooms figured out how to make the same molecule using entirely different chemistry. This is convergent evolution at the molecular level, like how wings evolved independently in insects, birds and bats, or how eyes evolved separately in vertebrates and ceopods. Similar solutions to similar problems arising through different routes. But convergent evolution of a complex molecule that is rare. Molecules are specific. You need precise enzymes to catalyze each step of synthesis. The fact that multiple mushroom lineages independently evolve, complete biosynthetic pathways for psilocybin suggests that psilocybin provides a strong evolutionary advantage. What advantage mushrooms produce psilocybin in their fruiting bodies? The parts we see above ground. The parts that animals eat. Psilocybin affects animal behavior. It causes altered perception, changes in mood, sometimes aversion. Maybe it deters herbivores. Eat this mushroom and you have a weird, unpleasant experience. You learn to avoid it, or maybe it attracts certain animals that help disperse spores. Eat this mushroom. Trip. Remember it vividly. Tell others where you found it. More attention means more spore dispersal. We do not know for sure, but the fact that natural selection favoured psilocybin production strongly enough for it to evolve twice independently tells us it matters to mushroom fitness. And the fact that it affects human brains. Producing profound psychological experiences is an accident. Humans were not the selection pressure. Mushrooms evolved psilocybin millions of years before humans existed. But the molecule happens to interact with serotonin receptors in mammalian brains. Our neurology is similar enough to whatever animals are eating these mushrooms that we feel the effects too. Sperm bots, tiny robotic devices that can be piloted through reproductive tracts. Researchers built them, tested them in artificial cervixes and uteruses, proved the concept works. The goal is fertility treatment, helping sperm reach eggs when natural motility is impaired. Male infertility often comes down to sperm that cannot swim properly, low motility, abnormal shape. The sperm are alive and genetically normal, but they cannot make the journey. A sperm bot is a microscopic device that attaches to a sperm cell and provides propulsion. Magnetic fields control it, guide it through the reproductive tract right to the egg. Then it releases. The sperm fertilizes normally. The bot is inert, biocompatible, eventually breaks down or is cleared by the body. In principle, it is elegant. In practice, there are challenges. Navigating the complex environment, ensuring the bot does not damage the sperm or surrounding tissue, making sure it releases at the right time. But the proof of concept is there. Sperm bots work in controlled laboratory conditions. This is the kind of innovation that sounds like science fiction until someone builds it. Then it becomes just another medical device. Weird initially, routine. Eventually, if sperm bots become a standard fertility treatment in 20 years, nobody will think twice about them. They will be as normal as in vitro fertilization is now. IVF was controversial when it started. Test tube babies playing God. Now, it is a multi-billion-dollar industry that has created millions of lives. A bright orange shark was discovered in the Caribbean. First of its kind, orange coloration in sharks is vanishingly rare. Most sharks are grey, brown, or muted colours that provide camouflage. This one is vivid orange, highly visible, and it has two rare genetic conditions, albinism and erythry. Albinism removes pigmentation. Erythism adds red pigment. Together, they produce the orange colour. The shark is essentially a double mutant, surviving despite being highly conspicuous in an environment where camouflage matters. Or maybe the orange coloration provides some unexpected advantage. Deep-water sharks are less reliant on visual camouflage. Their prey often hunt by sensing electrical fields or chemical cues. Being bright orange in the deep ocean might not matter, or it might even help with species recognition, mating, social signalling. We do not know. But the fact that this shark survived to adulthood suggests that being orange is not immediately fatal. Sometimes mutations that seem disadvantageous turn out to be neutral or even beneficial in specific contexts. A flower that smells like dying ants, Vincitoxicum nakayanum. a plant that has evolved to mimic the chemical signal ants release when they are attacked by spiders. Why to attract flies? The flies are attracted to the scent of dying ants, presumably because it signals a food source. Dead ants, spider prey, flies looking for carrion or other scavenging opportunities investigate. And while they are investigating the flower, they pollinate it, completely accidental from the fly's perspective, but precisely orchestrated by plant evolution. This is deceptive pollination taken to a bizarre extreme. Many plants deceive pollinators. Orchids that look like female insects, tricking males into attempting to mate with them and picking up pollen in the process. Flowers that smell like rotting meat to attract carrying flies, but mimicking the specific chemical profile of ants under attack that is exquisitely specialized. It requires the plant to produce a blend of volatile compounds that matches what ants emit, and it requires that flies have learned to associate that scent with food. The whole system is a three-way interaction. Ants, spiders, flies, plants, each doing their own thing, but the plant has inserted itself into the interaction, exploiting the fly's behavioral response to benefit its reproduction. Dogs can mentally categorize toys by function, not just recognize individual toys, categorize them. This comes from studies where dogs were given multiple toys and asked to retrieve specific ones. Some dogs could generalize. They understood that all balls are similar, all rope toys are similar. This is abstract categorization, not just memory, not just responding to names, understanding that objects belong to functional groups. This suggests more complex cognition than dogs are usually credited with. Not just trainable, not just responsive to commands, but capable of concept formation,